What's up, guys? Good morning. We are continuing the Khan Academy SAT problems. It's pretty early, not super early, but it's about 6 o'clock in the morning. A little tired for some reason, but it is what it is. And we are going to jump right into these problems where we are doing linear and exponential growth problems today. So I'm going to go ahead and jump over to shared screen. And by the way, on Instagram, if you guys are watching, jump onto my YouTube channel. Check it out so you can see the full problems here. So let's jump to share screen. Boom, and let's get right into it without any delay. Linear and exponential growth problems. And again, I'm seeing these problems for the first time, which is always part of the fun. Oops. Let's clear this. And let's do this guy. There we go. My assumption is we have to determine if something is either linear growth or exponential growth, which I'll explain in a second if that is the case. All right, here we go. Laxman. Laxman recently started a restaurant 32 weeks ago. So here are the weeks, and I don't know if this is cost. Let's see. The table above shows the number of customers. C, number of customers during the week, during the W-th week. Which of the following correctly explains the growth of customers with respect to W? Well, before we even read any explanation, look at what's happening. You could say it's adding 30, then it's adding 60, then it's adding 120, then it's adding 240. It looks like this is doubling every time, but now you might be tempted to say this is exponential growth because when you're doubling every time, it's exponential. But in fact, that's not what's happening. I don't think anyways, because look what's happening here. This is going from 1 to 2. That's a change of 1. This is going from 2 to 4. That's a change of 2. 4 to 8. It's a change of 4. So while these are doubling, the weeks are also doubling. So it looks like it's actually consistently going up by 30 every week, right? Week 3 would have been 90, then week 4 would have been 120. 5 would have been 150, 6 would have been 180, 7 would have been 210, 8 would have been 240. This looks like linear growth to me. Now it says the number of customers per week grew linearly. Okay, so I'm just going to go ahead and say linearly is going to be right. So I'm going to, there's C and D talk about exponential growth. Try to trick us. It's not exponential. The number of customers per week grew linearly because the number of customers per week increased approximately by 30 every week. And we already said that. We know that's right. The other one says 100. Let's go ahead and give this an answer. Boom, there we go. Next question. Question 2. Let's load it up here. And we've got, oh, this one came out nice and big. It's going to be very legible. It says, question 2 of 5, 12 grams of a chemical are added to a metal. The amount A in grams of the chemical remaining during a reaction with a metal plate decreases by 0.5 grams per second. If instead the plate were dissolved, okay, the amount A in grams of chemical remaining would decrease by half of itself every 4 seconds. How many grams greater is A than A with a little hat on top after 12 seconds? Interesting. Okay, so it's saying it's added to a metal, then the amount of chemical remaining during the reaction decreased by 0.5. Instead, if the plate were dissolved, okay, the amount A in grams of the chemical remaining decreased by half every 4 seconds. Okay, so let's do a little chart. So we want 12 seconds. So we'll do 1, 2, 3, 4, 5, 6, 7, 8. You don't have to do it like this, 9, 10. But I think this will be the easiest. So here's all our seconds. Whoops. All right. Now let's do A to kind of map this out a little bit. So it goes down by 0.5 every second. Let's just say that means it goes down 1 gram every 2 seconds. So this becomes, but it starts at 12, then it goes to 11, and then it goes to 10, and it goes to 9, and it goes to 8, and it goes to 7, and then after 12 seconds, it's at 6 grams. Now let's look at the other guy, with the little hat on top, where it decreases by, what was it? Where it decreased by half of itself every 4 seconds. So we're starting at 12. Oh, wow, okay. So we start at 12, and after 4 seconds, we're at 6. Then we go another 4 seconds to 8, and we're at 3. Then we go another 4 seconds, and we're at 1.5. You see how that works? It goes half of itself every 4 seconds. So these are the two values we're comparing. How much greater is 6 than 1.5? Should be 4.5. Right? If we just do that subtraction, let's go ahead and solve and see if that's correct. 4.5. Oops. Yes, and it's correct. Question number 3. Now, we could have actually not made a table there and actually kind of jumped ahead, figured it out based on an equation, but you don't always need to. That one I knew it wasn't going to take that long to set it up. Here we go. An old computer program which computes the nth Fibonacci number takes 0.05 microseconds to compute the first number. 0.05 to compute first number. After this, each number takes twice as long as the previous. So second would be 0.1, third would be take 0.2, second, so on and so forth. A computer engineer designs a new program. I'll say ... so we know. Makes a new program which takes just 0.8 microseconds to compute the first, which takes 0.8 microseconds to compute the first. Whoops, 0.8 first. And after this, each number takes 0.6 seconds longer than the previous number to compute. So then the next one is 1.4. Next one is 2. You see by the third, they kind of intersect. How much longer in microseconds does it take the old program to compute the 8th Fibonacci sequence compared to the new program? All right. You could use the formula for basically these are, one is a geometric series and one is a arithmetic series. So this is geo, this is arithmetic. I know these formulas because I was just working with the student the other day using them, but they're not the easiest to memorize. I mean, you know, it would take some practice. I'm not advocating memorizing them. So I'm gonna go ahead and just solve it. The formula makes it really fast, but we can do this pretty quickly. So look, I want to take, how much longer did it take the old program? So let's go, this is the old, right? Third, this is fourth, we got fifth, sixth, seventh, and eighth, right? So we're just doubling this one each time. So it becomes 0.4, and it becomes 0.8, then it becomes, oh wait, I'm sorry, yeah. Oh, these don't match up yet. I'm sorry, because that was 2 and that was 0.2. So 0.4, 0.8. Yeah, so I did that wrong. So 1.6, 3.2, and then 6.4. All right, so 8, it takes 6.4 microseconds. Here we'd have, I'm just going to keep it like this, 2, then we have 2.6. All right, we're going up by 0.6 every time. 30.2, 30.8, 4.4, and 5. Okay. So what's the difference? This is a difference of 1.4, and they even have the nice red herring here of 6.4, just in case if you're not paying attention. So how much longer does it take? It takes 1.4 seconds longer. So one very important to read the directions. I think I've read them correctly. Yes, and we are good to go. All right. Let's go ahead and knock this one out here. Question number 4. The equation above approximates the relationship wildlife veterinarians found between the amount of amount T of cortisol in micrograms per deciliter. Yikes. Okay, so this is some crazy equation, micrograms per deciliters. In a wild harbor seal's tears, see the amount S of cortisol in the seal's serum. So this is serum with that S, and this is in tears, T. So it already looks like the serum has way more cortisol just from this equation than the tears. Which of the following best describes the relationship between the amount of cortisol in a seal's tears and serum? And so they want to know, is it linear or exponential? I can tell you right off the bat, this is a linear equation. There's no exponent attached to T. Well, there is actually, it's an exponent of 1, but that means it's a linear equation. It's a linear relationship. So whatever says exponential, we don't care about this. We don't care about this. It is linear. Now let's read the details. It is linear because there is a 11.5 increase in S for every 0.1 increase in T. That is correct, actually. A is right. Let's just read B. It is linear because there is a 32 increase in S for every point. No. Why is this one right? This one is because an increase per this is actually slope. Slope is the value multiplying the variable. This is basically slope-intercept form. So 115 is the slope. Why does it say 11.5? Well, because it says per every 0.1. If it said for every 1, it'd be 115. So they're trying to make this a little tricky just by changing up the numbers. It doesn't make it tricky, actually. You just got to be careful. All right. We're good to go. We got one question left here. Let's give this one a shot. Number 5, the final of the day. Man, I'm not feeling so great. I think it's my allergies. Here we go. Question 5 of 5. R equals 35.7 plus 1.37 T. The equation above relates the urbanization rate R as a percent. So R, this is the urbanization rate as a percent in a particular country to the number of years since 2000. Okay, so obviously this rate is going up since 2000. And at 0, that means the year 2000. Which of the following statements best describes the relationship between the years and, again, okay, and since 2000 and the urbanization rate? Is this linear or exponential? No exponent on that T. Therefore, we know this guy is linear. It's an exponent of 1. So let's knock off exponential. What's the 2? C and D. These are both exponential. Let's knock those off. So these are crazy. So now it says it is linear because the urbanization rate increases by 1.37 each year. This is right because that's our slope. They're just trying to identify the slope. That's the change. Then we've got it is linear because the urbanization rate increases by, no. This is your y-intercept. This is the starting point. This is in 2000. That means that's where it was. So we're going to go with B. We're going to go with this. There we go. That's it. So we are done. Now let's turn back to our, whoops, where is it here? Where is my screen share? Oh, there it is. Okay. Let's go back here. Oops. All right, we are back. The camera is working good. So thank you guys so much for joining. I hope that was helpful. And again, we've got new tutorials for the Khan Academy SAT problems coming to you every morning around this time until we get through all the Khan Academy SAT problems. And then we'll have a new topic. So I hope this was helpful. If you like this, if you enjoyed this, please like the video. Make sure to subscribe below for more education videos, math-related content, and everything else from Scalar Learning. And if you have any questions, email me at Huzaifa@Scalar Learning. Thank you guys so much, and have a great rest of your day.